Hello viewers and welcome to a new STM32 World tutorial video. This video will be the second part of my music player. At the time of recording, the first part has not yet been published, but it will be published this week as video number 56 tutorial. So this will presumably be tutorial video 57 in the list of videos. In the first tutorial music video, which is here, has been recorded. We are essentially dealing with the I to S. That means how to play the audio that is building on top of an earlier video, which is this one, 55, which is the DMA dual sine wave out on an I to S, but it is using a slightly different I to S. So let's do a recap of the first part of this video, which is basically dealing with playing the audio. We are using this music or audio DAC, which is called the PCM 5102A, which is a Texas instrument, and they are readily available in a breakout board like this. And we are actually using that breakout board. I don't know if I can show it. Well, it is there behind the speaker, so it's a little hard to see, but sorry about that. So yeah, that is all covered in the first video. So in this video, we will be dealing with the second part, which is basically reading files from an SD card and parsing the WAV header and then sending that audio data out on the PCM. So let's start by looking at the previous example. The previous example is in the repository as STM32 World I to S dual sine. And it is doing something I have done a couple of times before. I did a video with pulse width modulation. I did using the internal DAC. Same principle, and it's basically calculating a sine wave. I'm not going into the detail of that. I'll just go through the previous project, the parts that are relevant for this part of the project. All this up here is related to the calculation of the sine wave, but we have this buffer, which is basically the DMA buffer we are using to send data to the I to S DAC, and that is about all that is relevant. We have the process buffer, which is the one that actually calculates the sine. Now, in the first video, I believe the video we have listed here on the front page, the 55, somebody complained, and rightfully so, that I did processing of the buffers in the callbacks. That is a bit rude, and while it worked and could be accepted because it was predictable, it is better to handle the loads stuff in the main loop. So what I'm doing here is I'm simply setting that a variable called DMA buffer to fill to the point that needs to be filled, and then down in the main loop here, whenever that variable is set, I call that process buffer. That means that the actual calculation of the sine wave will be handled in the main loop, and the interrupt just returns immediately, the double buffering interrupt. Another thing that is important for what we are going to do today is this part, and this part, set I to S frequency. Now, the I to S device that I'm using, the PCM 5102A, can accept data in different sample rates, 44, 100, is a common one. 48,000, 96,000. There are multiple that are typically used in WAV files that I'm going to play today. So it is important, rather than having to convert those frequencies on the fly, which would give an enormous overhead, it is much better to simply change that frequency. And it is possible to set that on the I2S, simply set the frequency to whatever. So this function will be used to change those frequency. And that is about all there is to the previous project. It will remain here as dual sign, and you can look at that whenever you want. But we are not going to use that today. We are going to create a new one, STM32 World I2S SDIO SD FAT. Probably that name should have been a little bit longer. So let's look at some of the changes. Well, I should mention at this point, and let me go back to showing the device here. Now I have a speaker, a little silly speaker I bought on AliExpress or whatever for no money at all. But I actually had a problem recording the audio. The headset I am normally using, which I am wearing here, is actually a nicely noise cancellating headset, because I'm in a somewhat noisy environment here, and it is really good at filtering out music. So it was almost impossible to hear any of the audio through this microphone. But I realized finally that the silly little camera, which is not a very good camera, that I used to record this part, actually have a built-in analog microphone, and it has absolutely no intelligence whatsoever. So it was much better to record the audio for that. It may pick up some of the noise and stuff, and as such it may not sound so good, but at least it should prove a point. There you go. So let's look at the changes. First, let's look at the STM32 CubeMX. Now, the main one is the I2S. That is completely unchanged from the previous video. We have some parameter settings here. We default to 96 kilohertz, but since we have the function, we can change this by carefully adjusting the I2S clock here to a point. We managed to get down to some very low error rates. So this will be 0.1% too fast. It will play 0.1% too fast, and with the other frequencies it's pretty much the same. As usual, in connectivity we have our UART configured. One change we are doing in this video is we are going to receive data from the keyboard as well. So I have enabled a DMA receive stream in here, and the SDIO has been enabled. Now, I'm not going to go through all the details, but before we look into the code here, let me just mention some videos that I have released before, and I really strongly, if you have not watched them, go back and watch these videos before, because they will show a lot of the stuff that I'm putting together again. First of all, look at the tutorial video 55, or I am 56 at the time you're watching this, which will talk about the I2S, and then you should go back and look at tutorial video number 16, which deals with UART and DMA idle detect, which is used to receive character data from a serial port. And you should also look at the FATFS SDIO videos. I'm not going to dig into the details of FATFS or anything like that today. I'm going to skip over that. So let's look at the code for this video player. So what are we actually doing here? Let's look at, you can see all the sign stuff has been taken out, but I do have a typedef struct which contain the format of the WAV files, and this format header is described in the, let's find that, we have it here. It's described in the data format header, what data is in this one. We will have the audio format, which we should have PCM. We should have one. Actually, it turns out it can also be 65,535, but that's besides the point. It depends on what tool you use to convert them. I converted the ones I have from MP3. Number of channels, 1 or 2, whether it's mono or stereo. Sample rate, and the sample rate is important because that is the rate we are going to use to configure the I2S speed. So these data are basically picked up from the we have a receive buffer from the UART, we have the I2S buffer, we have a, I call it do buffer this time. I don't know why I changed the name, but in the previous one I can't remember what I called it, doesn't matter. I have a total uptime, I have a buffers done, which is basically a way to calculate how many of these buffers I actually handle. I have my usual write redirect. Then I have a button callback. I actually did enable the button, but since I have a serial interface now, I'm not really using that. I have this method, which I have modified slightly compared to the previous one. In the previous one, I just tried to switch between I2S frequencies. In this one, if this is 0, I don't start it. I use that to stop the I2S. I simply call set I2S frequency with a 0, and it will stop the DMA transfers completely, which is how it should be. I have my process buffer. I'm going to get back to that. I have the exactly the same, the I2S DMA callbacks. I'll get back to that. And I have the process character where I receive characters from the UART. So you can see here I created 3 characters: E, this is gaming keys, up, down, and F, which is right. So I use F to switch to the next file, D to lower the volume, and E to increase the volume. The volume is just, I call it amplifier. It's just a 0 to 1 floating point that I multiply with the output sample value, and that way I can turn the volume up and down as I please. I am not going to go into this UART handling. That is handled in the earlier video so let's go down and look at the main, what we're actually doing here. We are starting the music player. We are showing the SD card information. We have the option of, we are mounting the disk, and I'm having a file called total uptime, which I use to keep track of how long has this been running forever since start, and I show that. And I update it every minute. I'll update that. Then I start the DMA, and I will I start the DMA receive. I also find the first file, which is a WAV file, and that's it. Then we are down in the main loop. In the main loop, I'm blinking a LED. I am waiting for a tick every second, and I had the option of printing out. I disabled that. You can see it here because it was just annoying. But you can enable it again for debug purposes. It will show how many buffers are done and the loop count and stuff like that. It's all good, and once every minute I update that file, which is called total uptime. And so now we get down to the meat. If we look up here, Where do I set that? Oh, it is actually set up in the front. Up the variable declaration, you can see open next file is set to 1. So by default, it will be set to 1. So down here in the main loop, we are waiting for open next file to be non-zero. Which it will be by default. And you can see, just to clarify, that open next file will be 1 by default, but when we're done this, it will then be set to 0. And then, of course, when a track is fully played, it will set that variable and it will open the next file. So we start by closing that music file if it's open. This one will fail quietly if it will return an error, but if I ignore that return, it will close if it is open. Then it will use find next to find the next file. Notice up here before we had the find first somewhere. Where's that? There, we find the first. That's probably, I'll kind of skip the first file, I guess. So it will find the next file, then it will open that file there, open it, and then it will parse the, we have that WAV format, which I declared earlier, the time def, and then we will call parse WAV header on that file. If that is okay. If it's not okay, if that fails, then it will immediately open the next file. So if one of these files cannot be parsed, it will just skip to the next one immediately. Otherwise, if it passes the header file, it will print out, it will set the frequency, and it will set that open next file to 0, so it won't do anything further until open next file is set to 1 again, and then it will repeat through this process. I forgot to mention up here, yes, if it doesn't find one, actually I discovered a bug in my code. I'll get back to that. If it doesn't find one, it will start all over again. So it'll find first, and then it'll go, once all the files have been gone through, then it will start all over again. I forgot to mention that. Then we simply have down here, we have the do buffer, and the do buffer basically process the buffer in the what used to be done in the I2S callback. So let's look at the parse header, and I'm not particularly proud of this parse WAV. However, it's quite a buggy, but I just did the bare minimum to make it work. So I am basically following, it's described here how these are spread out in the file, and it's the important part is I'm looking for that a string called WAV FMT. And at that point, I simply copy the data in because it is in the format that it needs, and that gets copied into that format structure. And the interesting part here is that I'm then looking, finally I'm looking for the data offset. And here's actually a little bit interesting. Now, I used to do this one, but it didn't work, where I'm looking for, I use str to find data, because the data will start with data as a string inside the file. But this didn't work, and the problem is that the header of a WAV file can contain zeros, and that means str cannot, any zero in buff will mean that that string is no longer, because it only handles strings, and that means it will not search for the rest. So this one would consistently fail. Let me put that in. There, but I I can search through it with simply search to mem compare and wait until I find data in the, and this one is searching binary, so it will work. It is probably not even slower than STI. It's probably the same, because I would have think that that does it the same way. When I find data, the interesting part is I know my data offset in the file, and if I can fail, if it doesn't fail, but if I find it, I will else seek to that point in the file. This means that if this one returns fr OK, then the file is open, the music file is open, and it has been seeked to the point where the data is starting. I will know that, otherwise it will fail, and that's fine. But if this one returns, I will have the information that I want, which is essentially the sampling rate, and the file will be open. So if we look down here at the end, open next file, you can see I parse WAV, however, I will print it out to let you know. I'll set the I to S frequency. The moment I set the I to S frequency, look up here, there, it will start the DMA transfer with the circular buffer, and at whatever frequency that file is, and that means the DMA layer will start getting data from those buffers, and that means we start getting the process buffer calls, and in the process buffer call, all I'm doing is I am reading a chunk of data that exactly fits the buffer. I see that we have how many bytes we actually read. I will fill those into a temporary buffer here. I'll calculate, I'll amplify, so that is how I handle the amplifier. I'll go through all the samples and multiply them with that amplifier value, and then I'll simply mem copy it into the target buffer, and if the byte reads are less than the buffer size, then I know the file is done. I can set the frequency to 0, that means it stops playing, and I can open next file, and the whole process repeats. That is all she wrote. That is all it takes. Now, it is important to realize that the format of a WAV file, and the reason I picked that so far, is exactly the same as I to S expects. So let's try to build this project. There. Let me go away so you can see the screen, and let me show the output, and then let me flash the output there. So as explained, it will start the player, it will show the SD card information, and it will search for the first file. It will also do that total uptime. It's been running for 16,395 minutes. It's probably been using that SD card for a number of projects, and I probably left it running overnight. And you can see it found a WAV file, the first WAV file here, which is the 1812/2. It read the header, and it concluded the data offset is 36. It seeks to that 36, and it will show a WAV format of 1, which is relevant. 2 channels is stereo, and a WAV frequency of 48,000 Hertz. So I'm setting the I to S sample frequency to 48,000, and that is all it takes. Now let's see. We have the device there. We can do that, and we can enable. It should be a little, it should probably get a little bit noisy now, but let me enable that microphone there, and let me try to switch the speaker on. So there we go, Tchaikovsky in all its glory. Now, if we look at this, we remember I had the EDF files. If I press D, you can see on the output it lowers the volume. So I can lower the volume all down to absolutely nothing. I can increase the volume. And you should also be able to see on the scope that the value changed. I can also change to the next file by pressing F. So that is Beethoven, no less, his ninth and final. So there you go. And I should mention before YouTube have a heart attack that these files are completely legal to use. Somebody might complain anyway, but I am absolutely sure that they are legal to use. There you go. I'm going to switch off my microphone first and going to switch off the speaker so we can have a little peace and quiet again. So there you go. It actually works. I got about 200 audio files on that SD card, and except one or two of them, they all play. I haven't really looked into the details of that again. So there you go. A music player on an STM32. Now, there's a few things I want to do before we end this video, because it's a little bit interesting to see where is the time actually being spent in this. Is it processing those buffers? Is it handling the SD card, or what is it? And a way to do that is actually to run a profiler on this. So let's, well, I'm not needed, I think. So let's try to fire this up in a debugger and see what is actually happening in this setup. So there we go. Debugger is running. Now I have enabled a tab down here called SWV, Serial Wire Viewer, statistical profiling. I have enabled the capture in the settings. I have enabled the PC sampling. So now let's try to, let me show the output there. Let's try to run it there. So you can see it started. It is now playing. Now I can show that by showing the device up there. It is actually, you can see first of all the LED is flashing, and you can see a little bit of stuff on the scope. There, that was a little louder. So yeah, it is working. Now let's try to pause it and see what is happening. And here comes the interesting profiling, statistical profiling. And you can see it spends 76% of its time in the main loop. It spends about 10% doing SD read. So that is actually one of the big things, is actually reading data from the SD card. It is expected that it's doing it quite often. It is quite possible that this can be optimized by matching the buffer size with a bigger buffer size, for example, matching the buffer size with the sector size on the SD card. I don't know, I haven't played with that yet, but it is worth looking into. You can see the process buffer. The overhead of actually multiplying with the amplifier takes 3% of the MCU time. We probably have that mem copy where we copy that stuff back, but that should also be within this process buffer. And you can see you have some SD MMC functions and stuff like that. But it would appear that most of the time in this is being spent in reading files from the SD cards. And this is the point where when you are a little bit closer to actually having a product, you would go through, you would comb through these and see where you can optimize your information where you can optimize the performance, all in the using the profiler and a good bit of common sense. But this pretty much matches what I would have expected. So I'm not too surprised about this. So it would be worth trying to optimize the SDIO and FATFS. It is quite possible that especially matching the sector size with the formatting of the SD card is probably going to improve dramatically. Now, am I going to make more videos in this series? Yeah, well, I mean, this I think is leaning itself towards a couple more videos. One thing, and I have perhaps already cheated a little bit, you see, I have that Spirit DSP MP3 decoder. I have not tried it yet, but it is here. It would be interesting to actually handle MP3 files directly. I think that would be very, very cool. It also leans itself towards having a display, so I can actually show the meta information from the files. That makes more sense once I have MP3 files. I can actually show the meta information in those MP3 files. That would be insanely cool as well. Right now I am actually dumping it out on the serial console. These files don't have any meta information because I converted them with SOX, I believe it's called, from MP3. MP3 had MP3 ID tags in them, but I skipped all that out and converted it to PCM. I could also use a tool called MPG321. That one includes meta information, but it converts to a different WAV format, the 65535, which is not the one I wanted here. Yeah, it's still very much a work in progress, but as you can see, and this in my opinion is the important thing here, is that once you have the different elements of this in place, like in this project, I used techniques that I have been using in earlier videos, like handling serial read and handling I2S and double buffering DMA and all that jazz. And once you have that, it actually becomes quite easy to fit the different pieces together and make this work. And I would say this audio player has been running overnight several times, and it works. The only thing that makes it not crash but stop is if it comes across an unparsable WAV file and end up setting the I2S frequency to 0. There it will stop, because it will never get to the point where it advances to the next file. So it'll just stop there because it's not reading the file, so it doesn't reach the end of the file. So yes, there is plenty of room for improvement, but you, dear viewers, wouldn't be watching this video if you didn't feel that you wanted to learn. And the way to learn is to get your hands dirty and poke around at this. So yeah, I mean, by all means add MP3 yourself, or make the header parser better. I am not particularly proud of the parse WAV header. That is really, really rough. And it could be improved a lot. So yeah, I would love suggestions. And actually the best way to make suggestions is to fork. Let's show you that. Here we go. If we go to GitHub and go to the STM32 World GitHub, the best way to do this is to actually go in and create your own fork of this project, and then you do the changes you want down in the project, which is, where is it? I2S, it's here, right? You do the changes and then you commit to your repository, and then you create what is known as a pull request. For me, it will show up here and I can see, well, somebody has done something, fixed a bug or whatever, and I can evaluate that pull request, and if it is reasonable, I'll just include it. It's as simple as that. I would probably recommend for the MP3, for example, if you want to add the MP3, don't modify this one because this one will stand with this video. So I will clone this project that has been described in an earlier video as well. How to clone duplicate project in STM32 Cube ID. I would suggest you look at that. Look at that video and you will basically just copy it. So there will be a new copy down here called STM32 World or whatever board you are using. I2S, SDIO, SD, FAT __ MP3, for example. And then modify that and make that the pull request. So I will see that somebody has created a new one. That would be ideal. I would love to see that. This is all about learning, including for me. I have never made a music player before, so everything I did in this with I2S and both the sine wave generation and the WAV file reading, it was all new to me, but it was what it is. So yeah, that is about it. As usual, if you like this video, please like and subscribe down there. It really helps the channel. I love comments, good and bad. And I usually respond to them. I mean, if rather than just giving it a finger down, if you don't like this video, I would like to know why you didn't like it, and it helps me improve the videos in the future. You can also join us on Discord and ask there. Our Discord is actually getting quite active. So have a look over at our Discord server and well, feel free to ask more complicated questions there than can be asked there. There are more people responding there. On the YouTube channel, it's just me. But on the Discord server, there's quite 3 or 4 really active guys there. So it is much better if you are there. So that is about it. As usual, dear viewers, have a wonderful rest of the day.